your senior OCI instructor at Oracle University. In this lesson, we'll explore how these metrics play a crucial role in monitoring the health, capacity, and performance of your Kubernetes cluster. As we delve into Container Engine for Kubernetes metrics, here are key takeaways. Picture this. We are not just keeping an eye on Kubernetes clusters, we are delving deep into the individual worker nodes and node pools, ensuring a holistic view of your entire cluster ecosystem. These metrics come to you in the OCI_OKE metric namespace, making it straightforward and accessible for your monitoring needs. It's not just about monitoring, it's about having the tools to diagnose and troubleshoot issues within your clusters and node pools efficiently. Like clockwork, default service metrics are posted every 60 seconds, a steady rhythm of data points per minute offering real-time insights. You can visualize your metrics by moving to the OCI console, selecting your specific cluster and clicking on metrics. It will open up a world of default charts. It's your visual dashboard for understanding your cluster's health and performance. In essence, Container Engine for Kubernetes metrics isn't just data. It's your power tool for effective cluster management. Let's dive into the details and unleash the potential of these metrics. Let's take a look at specifics of each available metric in the OCI_OKE namespace. To start with, we have the resource ID metric. It specifies the OSID of the resource under the microscope. Next up, we have the resource display name. It's a display name that adds a human readable touch, making our metrics more readable and easier to comprehend. Now let's talk about response codes. This metric captures the code sent directly from the Kubernetes API server, offering insights into the success or status of our server interactions. Response codes often form groups, and here we have response group. This categorization is based on the first digit of the response code, for example 2XX, 3XX, 4XX, and 5XX. These response codes simplifies our understanding of server responses. Shifting focus to clusters. Cluster ID brings us the OSID of the specific cluster in question. Moving down the hierarchy, node pool ID steps in. This OSID directs us to the exact node pool associated with our metric, enabling a granular examination of performance and behavior. Node state takes us into the world of compute instances hosting worker nodes. It's more than just active or inactive. It details the state of these instances, such as creating, deleting, updating, or even facing failures. Next up is node condition, revealing the condition of our worker nodes as perceived by the Kubernetes API server, whether it's ready, under memory pressure, or facing other challenges. This metric keeps us informed. Moving to infrastructure details, availability domain indicates the availability domain where the compute instance resides, a critical piece in understanding the physical location and redundancy of our resources. Finally, fault domain emerges as a metric, highlighting the fault domain where our compute instance is situated. This is pivotal for resilience and fault tolerance, giving us insights into the geographical dispersion of our resources. Each of these metrics is a powerful lens into the dynamics of our Kubernetes clusters, offering clarity and precision in our observability journey. Let's explore how to view default metric chart for a single Kubernetes cluster using the OCI console. Within the Metrics tab on the Cluster Details page, we find detailed charts for various metrics within the OKE namespace. Let's break down some key metrics. The first metrics that we get to see is the API server request count. This represents the number of requests received by the Kubernetes API server. Next up is the API server response count. It denotes the number of non-200 responses, specifically error responses, sent from the Kubernetes API server. And finally, we have the unschedulable pods. This metric indicates the number of pods that the Kubernetes scheduler is unable to schedule. Note that this metric is not available in clusters running versions of Kubernetes prior to version 1.15. I will now switch to OCI console and we will take a practical look at the default metric charts available for single Kubernetes cluster. I'm already logged into my OCI console. I'll move to the Kubernetes clusters service page. I'll select the first cluster on the list, which is OKE public demo 2. On the clusters details page, I'll scroll down and here we have the metrics section. Here we have the flexibility to adjust the time range. And as discussed in the lesson, we have the API server request metric. This represents the number of requests received by the Kubernetes API server. If I click on the data point and if I adjust the x-axis, you can notice that there were requests made to the Kubernetes API server. I'll click on close. And similarly, we have the API server responses metric. I'll click on the data point and adjust the x-axis. And as you can notice from the Kubernetes API server response chart, we have mix of responses from the 200 range to 300 as well as 400 range. I'll click on the close button here. And we also have a metric for unschedulable pod. This basically represents the number of pods that the Kubernetes scheduler was unable to schedule. And in this case, there were no such pods that were unable to schedule, which is why we don't see any data entry over here. To see metrics for a specific node pool or worker node, we must navigate to the respective tabs and click on the desired name. On the node pools metrics tab or the worker node metrics tab, we get to see different metrics such as node state. This metric reveals the number of compute nodes in different states. And we also have the Kubernetes node condition metrics. It showcases the number of worker nodes in various conditions as reported by the Kubernetes API server. I'll transition back to the OCI console and we will see the node pools metrics. I'll click on the node pools under the resources section and click on the pool name, which is pool 1. I will scroll down on the node pool details page and here we have the metrics resource. I'll click on metrics and this displays two metrics. One is the node state and the other one is the Kubernetes node condition. In our case, we have 5 nodes within this managed node pool and all the 5 nodes, as you can see on the y-axis, are in the active state as per the node state metrics and they are in the ready state as per the Kubernetes API server metrics. As we conclude our exploration of Container Engine for Kubernetes metrics, we've gained insights into critical metrics required for monitoring and optimizing the health of your Kubernetes clusters. Thank you for joining us in this video and I look forward to seeing you in the next one. Congratulations on making it this far. In this module, we'll cover the vital security practices for your OKE clusters on OCI. The importance of Kubernetes security cannot be overstated, especially in today's digital landscape where the integrity of your data and applications are paramount. We'll begin by understanding the significance of adding a service account authentication token to a kubeconfig file, followed by mastering access control in Container Engine for Kubernetes. Next, we'll navigate the intricate world of Kubernetes role-based access control, also known as RBAC, learning to grant cluster admin privileges and create specific roles and role bindings to manage pod and secret access efficiently. Secret management is a crucial aspect of Kubernetes security, and we'll learn best practices for managing secrets for Kubernetes clusters. Additionally, we'll dive into OKE image security, exploring techniques such as image scanning, signing, and enforcing use of signed images from Oracle Cloud Infrastructure Registry. But that's not all. We'll also tackle the vital topic of encrypting data at rest and in transit using various OCI services. From block volume service to the file storage service, we will explore different encryption methods to safeguard your data effectively. By the end of this module, you will gain a comprehensive understanding of Kubernetes security and compliance practices, empowering you to fortify your OKE clusters and secure your valuable resources within the cloud. So let's get started. Hello and welcome to this lesson on adding a service account authentication token to a kubeconfig file. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Let's get started. When you set up the kubeconfig file for a cluster, by default it contains an Oracle Cloud Infrastructure CLI command to generate a short-lived cluster-scoped user-specific authentication token. The authentication token generated by the CLI command is appropriate to authenticate individual users accessing the cluster using kubectl and the Kubernetes dashboard. However, the generated authentication token is not appropriate to authenticate processes and tools accessing the cluster, such as continuous integration and continuous delivery tools. To ensure access to the cluster, such tools require long-lived, non-user-specific authentication tokens. One solution is to use a Kubernetes service account. Having created a service account, you bind it to a cluster role binding that has cluster administration permissions. You can create an authentication token for the service account, which is stored as a Kubernetes secret. You can then add the service account as a user definition in the kubeconfig file itself. Other tools can then use the service account authentication token when accessing the cluster. In conclusion, we've explored the importance of adding a service account authentication token to a kubeconfig file, especially in scenarios involving CI/CD processes. This modification enhances security and enables automated tools to interact seamlessly with your Kubernetes cluster. In our next video, we will delve into practical examples, breaking down the steps to see this concept in action. Stay tuned for a hands-on walkthrough of adding a service account authentication token to a kubeconfig file. See you in the next video. Thank you for watching. Hello and welcome to this demo on adding a service account authentication token to a kubeconfig file. Let's get started. I have already logged into my OCI account and this is my OCI dashboard. I'll go to the Kubernetes clusters service by clicking on the Kubernetes clusters link from the recently visited section. For this demonstration, I'll be using the OKE public demo 2 cluster. And first thing is I'll ensure that I have the cluster access set up for this cluster. I'll click on the cluster name and click on the access cluster button. I'll copy the command to set up the kubeconfig file for this cluster and go to the next tab where I have the Cloud Shell terminal open. I'll paste the command here. Well, the config has been returned to our kubeconfig file and I'll quickly check the connectivity using the kubectl command. Well, this confirms that I'm connected to my OKE public demo 2 cluster, as it has returned the list of 5 nodes that are part of my managed node pool within the cluster. I'll clear the screen. Now the next step is to create a new service account in the kube system namespace. The command I'll be using is kubectl-n, which stands for namespace. And the namespace is kube-system. We are creating service account, and the name of the service account is kubeconfig-sa. I'll hit enter here. It says service account kubeconfig-sa created. Well, just for your information, creating a service account in the kube system namespace is recommended good practice. However, if you prefer, you can create the service account in another namespace to which you have access. Now the next step is to create a new cluster role binding with cluster administration permissions and bind it to the service account we just created. I'll use the command kubectl create cluster role binding. The cluster role binding name is add-on cluster admin, and I'll use the flag cluster role to specify the type of cluster role, which is cluster admin, and the flag service account to set up the service account information, which is kube system kubeconfig-sa. This is the service account which we created in the previous step. I'll hit enter. From the output, we can confirm that add-on cluster admin cluster role binding has been created. Now the next step is to obtain an authentication token for the kubeconfig-sa service account. And to obtain an authentication, we'll have to create a secret. I already have the manifest created. I'll open up the manifest file. This YAML manifest represents a Kubernetes secret resource that is used to store a service account token for the kubeconfig-sa service account within the kube system namespace. Let's break down the manifest. The API version here specifies the version for this Kubernetes resource, and in this case it is v1. Kind defines the type of Kubernetes resource. Here it is secret. Metadata contains metadata about the secret, such as its name, which is OKE kubeconfig-sa token. Namespace specifies the namespace in which the secret is created, which is kube system. Annotations is basically additional metadata in the form of key value pairs, and in this case the annotation is used to associate the secret with a specific service account, that is kubeconfig-sa. Type here specifies the type of data in the secret, and in this case it is kubernetes.io/service account token, indicating that this secret contains a service account token. I'll close the file. Now to create the service account token, I'll use the kubectl apply command and use the manifest file name, which is OKE kubeconfig-sa token.yaml. I'll hit enter. Well, it says the secret has been created. Now let's view the details of the secret by entering the following command. Kubectl describe secrets, name of the secret, which is OKE kubeconfig-sa token, and the namespace, which is kube system where the secret has been created. I'll go ahead and hit enter. The output of the command that we ran includes an authentication token, as you can see on the screen. It's a long alphanumeric string. I'll clear the screen here. And now we must obtain the value of the service account authentication token and assign its value to an environment variable. And the value must be decoded from base 64. With this command, I'm extracting the token value and decoding it using the base 64 decoder and setting it within the token environment variable. I'll hit enter here. And the prompt has returned successfully without any error, which means the token variable has been set with the service account authentication token. Now the next step is to add service account and its authentication token as a new user definition in the kubeconfig file, for which I'll run the command kubectl config set credentials, specify the service account name and use the token flag, and specify the environment variable where the service account token is stored. I'll hit enter. From the output, we can confirm that the user kubeconfig-sa has been set. Now to check the information of the current context that is used to access the Kubernetes cluster, I'll run the command kubectl config space get-context and hit enter. From the output, we can confirm that there is just one entry for the context, that is only one cluster is accessible using the kubectl. And under the auth info, we can confirm that the user that has access to the cluster for now is not the service account user that we just created. Also notice that asterisk here indicates that this is the current context used to access the Kubernetes cluster. Now the next step is to set the user specified in the kubeconfig file for the current context to be the new service account user that we just created. I'll use the command kubectl config set context and specify the --current flag and the --user equals to the kubeconfig-sa username, which we created in the earlier step. I'll go ahead and hit enter. And the output says the context has been modified. As you can notice, this is the current context from the previous output, and this has been modified now. Now to check the status of the modification, I'll run the kubectl config get context command again. And this time we get to see that the auth info has changed and the current user has been set to kubeconfig-sa, which is our service account user. Now to verify that the authentication works as expected, we will run a kubectl command to confirm that the service account user can be successfully authenticated using the service account authentication token. I'll simply run the kubectl get pods command and use the namespace kube-system. Well, the output has returned all the pods running in the kube system namespace. And since the command shows the pods running on the cluster, the service account user in the kubeconfig file has been successfully authenticated using the service account authentication token. Now we can distribute the kubeconfig file as necessary to enable other processes and tools such as CI/CD tools to access the cluster. And if you subsequently want to remove access to the cluster from the service account, we must delete the Kubernetes secret containing the service account authentication token. I'll be running the command kubectl-n kubesystem using the delete operation on secret with the name OKE kubeconfig-sa token. I'll go ahead and hit enter, and it says the secret has been deleted. Now let's check whether the service account user set in the current context is still able to access the Kubernetes objects. I'll run the command kubectl get pods-n and specify the namespace, which is kubesystem, and hit enter. And this command returns an error saying that you must be logged into the server, and this was an unauthorized access of getting information from the cluster. With this, we come to the end of this demo where we saw in practice how to add a service account authentication token to a kubeconfig file and then access cluster resources. I hope you found this demo useful. See you in the next one. Thank you for watching. Hello and welcome to this lesson on access control and container engine for Kubernetes. In this lesson, we'll find out about the permissions required to access clusters you have created using Container Engine for Kubernetes. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Let's get started. For most operations on Container Engine for Kubernetes clusters, IAM leverages the concept of groups. A user's permissions are determined by the IAM groups they belong to, including dynamic groups. The access rights for these groups are defined by policies. IAM provides granular control over various cluster operations, such as the ability to create or delete clusters, add, remove, or modify node pool, and dictate the Kubernetes object create, delete, view operations a user can perform. All these controls are specified at the group and policy levels. In addition to IAM, the Kubernetes role-based access control authorizer can enforce additional fine-grained access control for users on specific clusters via Kubernetes RBAC roles and cluster roles. Roles here defines permissions for resources within a specific namespace, and cluster role is a global object that will provide access to global objects as well as non-resource URLs such as API version and health endpoints on the API server. Kubernetes RBAC also includes role bindings and cluster role bindings. Role binding grants permission to subjects, which can be a user, service, or group interacting with the Kubernetes API. It specified a allowed operation for a given subject in the cluster. Role binding is always created in a specific namespace. When associated with a role, it provides users permission specified within that role related to the objects within that namespace. When associated with a cluster role, it provides access to namespaced objects only, defined within that cluster role and related to the role's namespace. Cluster role binding, on the other hand, is a global object. It associates cluster roles with users, groups, and service accounts, but it cannot be associated with a namespaced role. Cluster role binding is used to provide access to global objects, non-namespaced objects, or to namespaced objects in all namespaces. IAM and Kubernetes RBAC work together. IAM provides broader permissions, while Kubernetes RBAC offers fine-grained control. Users authorized either by IAM or Kubernetes RBAC can perform Kubernetes operations. When a user attempts to perform any operation on a cluster except for create role and create cluster role operations, IAM first determines whether a group or dynamic group to which the user belongs has the appropriate and sufficient permissions. If so, the operation succeeds. If the attempted operation also requires additional permissions granted via a Kubernetes RBAC role or cluster role, the Kubernetes RBAC authorizer then determines whether the user or group has been granted the appropriate Kubernetes role or Kubernetes cluster roles. It's common to define custom Kubernetes RBAC roles and cluster roles for precise control. To create these, user must have existing roles or cluster roles with equal or higher privileges. By default, users don't have any RBAC roles assigned, but there are default roles like cluster admin for super user privileges. In the upcoming videos, we'll delve into practical demonstrations of Kubernetes RBAC, providing a hands-on exploration of the concepts we discussed. Stay tuned for an immersive learning experience. I'll see you in the next video. Thank you for watching. Hello and welcome to this demo on granting the Kubernetes role-based access control cluster admin cluster role. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Let's dive in. I'm already logged into my OCI console and this is my OCI dashboard. For this demonstration, I already have the required access to create the Kubernetes RBAC roles and cluster roles. The user account using which I'm running this demonstration is part of the tenancies administrator group. You must ensure that if you are following the demo, you must be part of the tenancies administrator group, or you must have the required access to create Kubernetes RBAC roles and cluster roles. Also remember, the user to which you want to grant the RBAC cluster admin cluster role must not be an OCI tenancy administrator, If they are an OCI tenancy administrator already, they do not require the Kubernetes RBAC cluster admin cluster role. For this demonstration, I've already logged in into another browser as a user which is not part of the administrator group. The user is Krisha. I'll switch back to the browser where I'm logged in as tenancy administrator. For this demonstration, I'll first go to the Kubernetes clusters service page, and I'll be performing the demonstration on the OKE public demo 2 cluster. I'll click on the cluster name. And first thing that I must ensure is I have the access to the cluster. I'll click on the access cluster button, and I'll copy the command to set up the kubeconfig file to access this cluster. I'll head back to the next tab where I have the Cloud Shell terminal open. I'll paste the command here and hit enter. Well, a new config has been returned to our kubeconfig file. I'll cross check the same using kubectl get nodes command. The output has returned the list of 5 nodes which are part of the OKE clusters, pool 1. Now to grant the Kubernetes RBAC cluster admin cluster role to user Krisha, I must enter the following command. The command is kubectl create cluster role binding, provide a name to the cluster role binding, and then specify the cluster role, which is cluster-admin, and you must provide the user OSID to the user flag. I'll go ahead and edit the placeholders. Krisha_clst_admin is the name of the cluster role binding, and we must provide the user OSID. I'll go back to the other browser where I'm logged in as user Krisha. As you can notice, the profile says Krisha. I'll click on my profile, and from the user information tab, I'll copy the OSID of the user, which is a non-administrator user. I'll go back to the WordPad editor and paste the user OSID here in the command. Now, before I go ahead and run this command and provide cluster admin access to Krisha, I'll quickly demonstrate that Krisha is unable to access the Kubernetes cluster and its resources. I'll go back to the previous tab and go to the Kubernetes cluster service. I'll go ahead and click on the cluster name on which we are performing this demo. I'll click on the access cluster button and make sure that we have set up the kubeconfig file for Krisha user. We'll go ahead and paste this command here and hit enter. Well, it says the config has been returned to kubeconfig file for user Krisha. Now, if I go ahead and run kubectl get nodes command, you'll notice that we have received an error from the server which says forbidden, and the user Krisha, this is the OSID of user Krisha, cannot list resource node in API group at the cluster scope. Now I'll go back to the browser where I am logged in as an admin. As you can see, I've navigated back to Mahendra Mehra account, which has got an administrator privilege. I'll copy the command and paste it in the Cloud Shell terminal. With this command, I'm granting user Krisha the cluster admin cluster role. I'll go ahead and hit enter. Well, the output says Krisha_cluster_admin has been created, which means the cluster role binding is in place. Now, if I go back to the user Krisha's account, and if I rerun the kubectl get nodes command now, notice that I'm able to fetch the node details from the cluster. That's because user Krisha is now granted the cluster role, which is of type cluster admin. Now, with the cluster admin role, user Krisha can also create resources within the Kubernetes cluster. I'll clear the screen here and let me quickly demonstrate creation of a deployment using the user Krisha account. I'll run the command kubectl create deployment. The deployment name is nginx project, and the image that we'll be using to run the containers is nginx. I'll hit enter, and it says deployment nginx project created. I'll run the kubectl get all command, and from the output we can notice that the deployment nginx project is getting created. The nginx pod for the deployment nginx project is in container creating state. I'll rerun the command. Well, from the output, we can notice that the deployment is up and running as well as the pod within the deployment. This confirms that user Krisha has received the cluster admin cluster role and is able to list and create resources within Kubernetes cluster. Now I'll demonstrate you how to delete the cluster admin cluster role that we set up for user Krisha. I'll navigate back to my browser where I'm running as an administrator and simply run the command kubectl delete cluster role binding and provide the name of the cluster role binding that we created, which is Krisha CLST admin. There you go. I'll go ahead and hit enter. And the output confirms that the cluster role binding Krisha _ cluster _ admin is deleted now. If I switch back to the browser where we are running as user Krisha, and I'll first clear the screen. And now if I run the command kubectl get all, you can notice that we are receiving error from the server as the user Krisha is forbidden from accessing any resources within the cluster. With this, we come to the end of this demo where we saw how to grant and revoke Kubernetes RBAC cluster admin cluster role for an IAM user in OCI. I hope you found this demo useful. See you in the next one. Thank you for watching. Welcome back. Let's begin from where we left off in the last part. Now I'll show you how to create Kubernetes role and role binding to enable an IAM group to read pods in a cluster. It's pretty straightforward. I will open up the manifest file that I already have in place. Everything remains the same, just that the kind now is changed to group instead of user. And here we need to provide the OCID of the user group to which we are allowing the access. This is the OCID of my OCI developer group, which I had shown you at the start of the demo. I'll close this file and I'll go ahead and apply this manifest and hit enter. And the output says the pod reader KS role created as well as the pod reader KS role binding created for the group OCI developer group. Now, as we know that user Krisha is part of the OCI developer group, I'll go back to the account where I'm logged in as user Krisha. And now if I run the kubectl get pods -in kubesystem command, I'll have the access to the Kubernetes resource, that is pod, within the cluster kubesystem namespace. From the output, we can see that we get the list of pods running in the kubesystem namespace. With this, we come to the end of this demo where we saw how to create a Kubernetes role and role binding, firstly to enable a user and then to enable a group to read pods in a cluster. I hope you found this demo interesting. See you in the next one. Thank you for watching. Hello and welcome to this demo on creating a Kubernetes role and role binding to enable a user and group to read pods in a cluster. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Let's dive in. I'm already logged into the OCI console, and for this demonstration, I'll be reusing the user which I created in the previous demo, that is user Krisha, which is a non-administrator user. For this demonstration, I've created a user group and placed user Krisha within that group. I'll quickly show it to you. I'll go to the navigation menu, click on Identity and Security, go to Domains, move to the root compartment and select the default domain. I'll click on Groups. I have created the group called OCI Developer Group. And I have added user Krisha to this group, which is a non-administrator user. I've also created a new OCI policy that grants this group the cluster use permission on the cluster. I'll go back to the navigation menu and click on Identity and Security, click on Policies. And within my root tenancy, I've added this policy, OKE RBAC demo, where I have allowed the OCI developer group to use cluster in tenancy. You can also restrict the policy for this group to use clusters in a particular compartment. I've also allowed OCI developer group to use Cloud Shell in the tenancy. I'll now navigate to the browser where I'm logged in as user Krisha. And let me quickly demonstrate that user Krisha has got no access to the cluster that we are performing this demo on. If I do kubectl get pods command and provide the namespace, which is kube system, and hit enter, it says the user is forbidden from accessing pods information in the namespace kube system. Now I'll switch back to the browser where I'm logged in as an administrator and head to the next tab where I have opened up the Cloud Shell terminal. I already have created a manifest to define a Kubernetes RBAC role and role binding, which will enable this new IAM user account to list pods in the kube system namespace. Now remember, for this demonstration, I'll be showing you two versions where you can allow an individual user to access pods within the Kubernetes namespace. And I'll also demonstrate how to allow a group to access particular resources within cluster. For this demonstration, I'll firstly demonstrate how to allow a new IAM user to read pods in a cluster by creating RBAC role and RBAC role binding. I've already created a manifest that defines this role and role binding. I'll open up the manifest file. This is the manifest where we have defined the role and role binding for user Krisha, which allows the user to access the Kubernetes resources. Let's break down the manifest. Here the kind indicates that this is a role. API version specifies the version of the RBAC API being used. Metadata contains information about the role, including its name, which is pod reader KS, and the namespace, which is kube system. Rules describes the permission granted by this role, where API groups specifies the API group to which the rules apply, and in this case it's an empty string, which means the core Kubernetes API group. Resources define the Kubernetes resources for which the role grants permission, and here it's pods. Verbs specifies the allowed actions on the specified resources. The role allows get, watch, and list operations on the pod. We then have the definition for role binding, where kind indicates this is a role binding. API version specifies the version of the RBAC API. Metadata contains information about the role binding, like its name, which is pod reader case role binding, and the namespace to which it belongs, that is kube system. Subjects defines the entities. Here the kind is set to user, which means this role binding is for a user. And name here specifies the name of the user, where we have supplied the value as the OCIR for our user, Krisha. API group specifies the API group of the referenced role binding. Role ref refers to the role that the binding applies to, where the kind is set to role and the name of the role is specified, which is pod-reader-ks. As we can notice, at the beginning we have the same name set for our role, which is pod reader ks. And again the API group specifies the API group of the referenced role. So to sum it up, this configuration creates a role name pod reader ks in the kube system namespace, granting permissions to perform get, watch, and list operations on the resource pod. The role binding, which is pod reader ks role binding, associates a specific user, that is user Krisha in this case, whose OCID we have specified. The role binding associates user Krisha with the role pod reader ks in the kube system namespace. User Krisha will now have the specified pod related permissions within the specified namespace. I'll close this file and go ahead and apply this manifest to our Kubernetes cluster. I'll use the command kubectl apply space -f and name of the manifest, which is pod reader user.yaml. Well, from the output, it is confirmed that the pod reader KS role is created and the pod reader KS role binding is created. Now, if I go back to the account where I'm logged in as Krisha and hit the kubectl get pods -n kubesystem command, I'm able to fetch the list of pods running in the kube system namespace. Now I'll switch back to my admin user and let's go ahead and delete this user role. I'll use the command kubectl delete instead of apply and hit enter. The output says user role and role binding are deleted now. If I head back to the user Krisha, I'll clear the screen first and run the kubectl get pods -n kubesystem command. It will present me with an error saying that I'm forbidden from accessing the resources in this cluster namespace. I'm back to my administrator account and I'll clear the screen. Now, since this video is getting a bit longer, I'll pause here and we'll continue in the next part. Hello and welcome to this demo on creating a Kubernetes cluster role and cluster role binding to enable users and groups to list secrets in a cluster. Let's get started. I'm logged in into the user account Krisha, which is a non-administrator user account. And first let's check if the user Krisha has access to the secrets within the Kubernetes cluster by running the command kubectl get secrets and using the all namespaces flag. I'll hit enter and we can notice that user Krisha, from the output it's clear that user Krisha is forbidden from accessing or to say list resource secrets in the API group, which is the core Kubernetes API group. Now I'll navigate back to the OCI console where I'm running the account as an administrator user. I'll clear the screen. Now to allow the IAM user Krisha to list secrets in the Kubernetes cluster, I have the manifest file already in place. I'll open up the manifest file. And this is the definition to create cluster role, where we have specified the kind as cluster role. The metadata specifies the name of the cluster role, which is secret reader, and the rules define the API group, which is empty string. That means for the core Kubernetes API group, this applies. And the resources is set to secrets, where the actions that are allowed are get, watch, and list on the resource secrets. In the next part, we have defined the kind cluster role binding. The name of the cluster role binding is reader secrets global and the subject is defined as a user, and I have already specified the OSID of user Krisha. And the role the cluster role binding is referring to is the cluster role that we have defined at the top of this manifest with the name secret reader. I'll close this file and go ahead and apply this manifest to our Kubernetes cluster using kubectl apply command. I'll go ahead and hit enter and the output says the cluster role secret -reader created as well as the cluster role binding read secrets global created. Now I'll switch back to the browser where I'm logged in as user Krisha, and if I rerun the command kubectl get secrets, I'll go ahead and hit enter. And from the output, we can see the list of secrets that are defined in different namespaces. There are 3 we can see in the default namespace, and there are 4 secrets that are created in the kube system namespace. Now for the part 2 of this demo, where we will set up access for an IAM group to list secrets in Kubernetes cluster, I'll first go to the browser where I'm logged in as administrator. And I'll first delete the cluster role and cluster role binding that we just created. I'll replace the apply command with delete command. And this deletes the cluster role and role binding we created for user Krisha. I'll clear the screen and open up the manifest for the user group that I already have in place. The only thing that changes within this manifest is the subject field, where we have specified the kind as group and replace the user OSIT with the group OSIT. Now remember, user Krisha is part of this group, OCI developer group, whose OSIT I have specified in this manifest. I'll close this file, and before I apply this manifest to the Kubernetes cluster, I also want to demonstrate that since we deleted the cluster role and role binding for user Krisha will no longer have access to the secrets in all namespaces within the Kubernetes cluster. I'll clear the screen, and if I rerun the command kubectl get secrets, we'll encounter an error message. Alright, I'm back to the Cloud Shell where I'm logged in as an administrator. Now I'll go ahead and apply this manifest, which allows the group to have access of cluster resources using the cluster role and cluster role binding. I'll hit enter. It says the cluster role and role binding has been created. Now if I go back to the user Krisha account, and since user Krisha is part of the group which I have specified in the manifest, user Krisha must have access to all the secrets created in all the namespaces within the Kubernetes cluster. There you go. We can see the same list of secrets being displayed on the screen, but this time as part of a group that has the permission to view the cluster resources on a global scale. With this, we come to the end of this demo where we saw how to create a Kubernetes cluster role and cluster role binding to enable users and groups to list secrets in a cluster. I hope you found this demonstration useful. See you in the next one. Thank you for watching. Hello and welcome to the lesson on managing secrets for Kubernetes clusters. In this lesson, we'll explore essential methods to secure and handle sensitive information within your Kubernetes clusters, ensuring a robust security posture. Let's dive in. When creating Kubernetes clusters using OCI Container Engine for Kubernetes, there are two fundamental approaches to store application secrets. We can opt for storing and managing secrets in an external secrets store accessed seamlessly through the Kubernetes Secrets Store CSI driver, that is secrets-store.csi.k8.io. Alternatively, we have the option of storing Kubernetes secret objects directly in etcd. Let's dive into the first method of storing secrets in an external secret store accessed through the Kubernetes Secret Store CSI driver. This integration allows Kubernetes clusters to mount multiple secrets, keys, and certificates into pods as volumes. The Kubernetes Secrets Store CSI driver facilitates seamless integration between our Kubernetes clusters and external secret stores. With the Secret Store CSI driver, our Kubernetes clusters can mount and manage multiple secrets, keys, and certificates from external sources. These are accessible as volumes, making it easy to incorporate them into our application containers. OCI Vault is a notable external secrets store, and Oracle provides the Oracle Secret Store CSI driver provider to enable Kubernetes clusters to seamlessly access secrets stored in Vault. Now shifting our focus to the second method, that is storing secrets as Kubernetes secrets object in etcd. In this approach, we store and manage our application secrets using Kubernetes secret objects. These objects are directly managed within etcd, the distributed key value store used for Kubernetes cluster coordination and state management. In OKE, etcd reads and writes data to and from block storage volumes in OCI block volume service. By default, OCI ensures security of our secrets and etcd data by encrypting it at rest. Oracle handles this encryption automatically, providing a secure environment for our secrets. Oracle takes responsibility for managing the master encryption key for data at rest, including etcd and Kubernetes secrets. This ensures the integrity and security of our stored secrets. If needed, there are options for users to manage the master encryption key themselves. As we conclude, managing secrets is a critical aspect of maintaining a secure Kubernetes environment. In this lesson, we covered two robust methods: utilizing an external secret store with the Kubernetes Secret Store CSI driver and storing secrets as Kubernetes secret objects in etcd. I hope you found this lesson useful. See you in the next one. Thank you for watching. Hello and welcome to this lesson on OKE container image security. In the dynamic landscape of containerized applications, ensuring the security of containerized images is paramount. Let's understand the essential characteristics that container images must possess to fortify the security posture of your applications. Security first. It is not uncommon for the operating system packages included in images to have vulnerabilities. Managing these vulnerabilities enables you to strengthen the security posture of your system and respond quickly when new vulnerabilities are discovered. Diving deeper into the concept of security first, let's explore why this principle is crucial for container image security. You can set up Oracle Cloud Infrastructure Registry, also known as Container Registry, to scan images in a repository for security vulnerabilities published in the publicly available Common Vulnerabilities and Exposure database. To perform image scanning, Container Registry makes use of the Oracle Cloud Infrastructure Vulnerability Scanning Service and Vulnerability Scanning REST API. When new vulnerabilities are added to the CVE database, the Container Registry initiates automatic rescanning of images in repositories that have scanning enabled. You can gain valuable insights into each image scan conducted over the past 13 months. This includes an overview of the number of vulnerabilities detected and an overall risk assessment for each scan. Additionally, you can delve into comprehensive details of each scan, featuring descriptions of individual vulnerabilities, their associated risk levels, and direct links to the CVE database for more comprehensive information. This historical and detailed data empowers you to monitor, compare, and enhance image security over time. You can also disable image scanning on a particular repository by removing the image scanner. The next characteristic is unaltered integrity. For compliance and security reasons, system administrators often want to deploy software into a production system only when they are satisfied that the software has not been modified since it was published, compromising its integrity. Ensuring the unaltered integrity of software is paramount for compliance and security in production environment. Let's delve into the mechanisms that guarantee this integrity within the context of Oracle Cloud Infrastructure. Firstly, image signatures play a pivotal role in not only verifying the source of an image, but also ensuring its integrity. Oracle's container registry facilitates this process by allowing users or systems to push images and sign them using a master encryption key sourced from the OCI vault. It's worth noting that an image can have multiple signatures, each associated with a distinct master encryption key. These signatures are uniquely tied to an image OSID, providing granularity to the verification process. Furthermore, the process of image signing mandates the use of an RSA asymmetric key from the OCI vault, ensuring a robust and secure validation of the image's unaltered integrity. Moving on, in the realm of container images, the third crucial characteristic is ensuring trusted sources, vital for compliance and security considerations. System administrators need the assurance that the software being deployed in a production system originates from a source they trust. Let's explore the mechanisms that enforce this trust within OCI. Firstly, signed images play a pivotal role, providing a means to verify both the source and the integrity of the image. To further strengthen this, administrators can create image verification policies for clusters, specifying which master encryption keys must have been used to sign images. This enhances security by configuring Container Engine for Kubernetes clusters to allow the deployment of images signed with specific encryption keys from Oracle Cloud Infrastructure Registry. As a result, users or systems retrieving signed images from OCIR can trust the source and be confident in the image's integrity. To wrap up, in this lesson, we covered prioritizing security through active vulnerability management, ensuring unaltered integrity, and relying on trusted sources for robust container image security. I hope you found this lesson interesting. See you in the next one. Thank you for watching. Hello and welcome to this demo on scanning container image for vulnerabilities. My name is Mahendra Mehra and I am your senior OCI instructor with Oracle University. In this demo, I'll be showing you how to perform a vulnerability scan on a container image that has been pushed to the Oracle Cloud Infrastructure Registry using the vulnerability scanning service. By the end of this demo, you will be able to identify potential security risks in your containerized applications and take appropriate measures to ensure their security and reliability. So let's get started. Having signed into my Oracle Cloud account, this is my OCI console. Let's review the policies in place for the vulnerability scanning service. I'll go to the navigation menu and click on Identity and Security. Go to the Policies page. I'll select the parent compartment for my CTD OKE compartment, which is Mahendra. And here I've created a policy named Manage Repo VSS, where I have the policies in place to manage repos and vulnerability scanning service. I'll open up the policy for you. And these are the policies in place, where the first two policy is allowing the user group which I'm part of to manage repos in the compartment CTD OKE, as well as to manage the vulnerability scanning service family in the compartment CTD OKE. Additionally, there is a service level policy allowing vulnerability scanning service to read repositories in compartment CTD OKE. These three policies are essential for running this demonstration. Now let's go back to the home page. And as part of this demo, I'll go ahead and create a container repository. I'll click on the navigation menu, go to the developer services and click on container registry. The registry that I'll be creating is in the CTD OKE compartment. I'll select the compartment from the list scope section. Currently, there is one repository in place with the name Mahendra/guestbook. I'll click on create repository and create a new public repository. I'll go ahead and set up a name which is unique across the tenancy. Repository name is demo/nginx. I leave the tag key value field as blank and click on create. As you can notice, the repository demo/nginx is created and the type of access is set to public. And from the repository information page, we can notice that the add scanner button is enabled, which means when you create a new repository, the repository by default has scanning disabled in it. And to enable it, we must click on the add scanner button. I'll go ahead and click on add scanner, and this opens up add scanner to repository window. Target name is optional. We'll still go ahead and provide a name to it. Description is optional, but we must make sure that we have chosen the right compartment for this scanner, which in our case is CTD OKE. And in the scan configuration window, we must go ahead and select create new scan configuration, or you can opt for an existing scan configuration. Since this is our first go, I'll select the create new scan configuration and give it a name. Make sure we create the scan configuration in the compartment where we have the permission to work in. In my case, it is CTD OKE. I'll go ahead and click on create. It says the scan recipe OCIR scan config was created successfully, as well as the scan target was created successfully. Now, since this repository has scanning service enabled, we get to see the button which says remove scanner. Now I'll push an nginx container image to this repository, for which I have already opened up the Cloud Shell terminal on a different tab. I'll first use docker login to log in to my OCIR repo. Command is docker login space phx.ocir.io. phx is the region key for the region I'm operating in, which is US West Phoenix. I'll go ahead and hit enter. Well, the username is basically your tenancy namespace / separated by your username, and it is auto-populated in most of the cases. I'll go ahead and hit enter. And as part of password, we need to provide the authentication token. I'll go ahead and paste my authentication token. Make a note that the password string is not visible on the screen, not even in terms of asterisks. I'll go ahead and hit enter. And it says login succeeded, which means I'm successfully logged into my OCIR repo. Now I'll run a docker pull command to pull an nginx image. I'll pull the nginx latest image. Well, it has pulled an nginx image with the latest tag. I'll run the docker images command to cross check. Yes, the nginx image is downloaded to our local repo with the size 187 MB. I'll clear the screen here and rerun the docker images command. Now I'll have to push this image to our OCIR repository that we just created, for which I'll have to first tag this image using the docker tag command. To tag the image, I'll use the docker tag command followed by the image ID, which I'll be tagging, that is the image ID of my nginx latest image. And here I've defined the fully qualified domain name for our OCIR repo, which is regionkey.ocir.io / the tenancy namespace / the repository name, which is demo/nginx:\latest. I'll go ahead and hit enter and rerun the docker images command to see if we have tagged the nginx latest image. And as you can notice, we have two images now in the local repo, and they both belong to the same image ID, as this is only the tagged version of the original image. Now I'll push this tagged image to the OCIR repo by running the docker push command and provide the path. I'll copy this name and paste it here. Enter. And since I was already authenticated to my OCIR repo, I'm able to push the Docker image, and the push operation has completed successfully. Now let's check if the image has been pushed to the OCIR repo. I'll go back to the previous tab and hit a refresh. Okay, so after the refresh operation, I'll click on the drop down under the repositories and images field. And if you notice, we have the Nginx latest image showing up in our demo Nginx repository. I'll click on the image name, and we can view the image information in the image information tab. Now, since we had already enabled scanning for this repository, any new image that we push to this repository will automatically be scanned by the vulnerability scanning service. To view the scan results, we will click on the scan results tab in the image information page, and I'll click on the scan results tab here. And if you notice, we have an entry for the scan result which says the risk level is set to high for this image, and there are 20 issues found with this Nginx image. And we also can see the timings for the scan, when it was started and when the scan completed. Now to view the scan results, including specific vulnerabilities in the CVE database detected in the image, I'll click on the actions menu, that is this 3-dot, and click on view details. This lists out all the issues detected in the container image along with the risk level categorization as high, medium, and low. At times you also see the risk level as critical. We also get to see the description for each issue that has been encountered within this image. To read more about any particular CVE or issue, we can click on this hyperlink, and it takes us to the nvd.nist.government's website where all the CVEs are listed. This is the National Vulnerability Database page where you can read more about the CVE in detail, its description, its severity level, the base score assigned to this vulnerability, and more, such as the solutions and advisories. We'll go back to the previous tab and close this window. Now let's explore the vulnerability reports by going to the navigation menu, and I'll click on Identity and Security and click on Vulnerability Reports in the Scanning section. The Vulnerability Scanning Service categorizes problems in these risk levels. You can go to the filter section and click on the risk level, where critical is the most serious problem detected, which should be your highest priority to resolve. High is the next most serious problem. Then we have medium, problems that are less serious, and low for the problems that are still less serious. I'll go ahead and filter all the CVEs based on high risk level. If I select high, you can see all the reports from the risk level that have been tagged as high. The last entry here is from the latest scan. Additionally, if you want to view more detail about the common vulnerability exposures listed in this window, you can simply click on the Actions menu and click on View Details. This opens up the Vulnerability Report Details page for the vulnerability we selected, where in the information bar we can see the threat associated with this vulnerability, as well as the recommended solution to resolve this issue. We can also export the vulnerability report, and that's straightforward. Just click on the Export CSV button, and this will download the vulnerability report in a CSV format. I'll click on Save, and let's open the report. And this is how you can view the vulnerability reports offline. And this is the vulnerability report of all the vulnerabilities detected over time for the images that have been pushed into the OCIR repos within the CTD-OKE compartment that had scanning enabled. I'll close this report. With this, we come to the end of this demo where we saw how to scan container images for vulnerabilities within the Oracle Cloud Infrastructure Registry service. I hope you found this demo interesting. See you in the next one. Thank you for watching. Hello and welcome to this demo on Sign and Verify Container Image for Security. My name is Mahindra Mehra and I am your Senior OCI Instructor with Oracle University. Let's dive in. In this demo, we'll take a look at how to sign and verify container images for security, ensuring that they have not been modified since they were published and maintaining their integrity throughout their life cycle. In the interest of time for this demonstration, I've already created an OCI vault, and within the vault I've created a master encryption key using the RSA key shape. During this demonstration, I'll be pulling an Nginx image of an older version from the Docker Hub repository, and we'll be tagging it and we'll push that image to the container registry repository which we have already created. And once we push the Nginx image to the container registry repository, we will create an image signature using the OCI CLI and ensure that the image within the OCIR is signed. I'll now navigate to the OCI console. I'm already logged into my OCI console and this is my OCI dashboard. First up, I'll show you the OCI vault which I've already created for this demonstration. I'll go to the navigation menu and click on Identity and Security. Here under the Key Management and Secret Management section, I'll click on Vault. Under the CTD OKE compartment, I already have a vault created with the name Image Signature Demo. I'll click on the vault. This opens up the vault details page where under the master encryption keys, I already have two master encryption key, but the one that I'll be using for this demo is MEK-demo. And from the protection mode, you can notice that HSM is the protection mode selected, whereas the algorithm that I chose for this key is RSA. To create a key, we must click on the Create button and make sure that you are creating the key in the right compartment where you have the permissions to work in. The protection mode chosen is HSM. You can provide a valid name to your key and make sure that the key shape algorithm you choose is RSA, which allows you to sign and verify images. The key shape length is 2048 bits. We'll leave it to the default and click on Create. In my case, I'll click on Cancel as I already have a key which I'll be reusing. To create the image signature, we will need specific details such as the master encryption key OCID and the key versions OCID. I'll click on the master encryption key which we'll be using for this demo, which is MEK-demo. And I'll copy the master encryption key OCID from the key information tab. I'll save this information in a notepad file. I'll also copy the key versions OCID which is listed in the versions section. I'll copy it from this location and paste it in the notepad file. And like I mentioned, I already have an OCI repository from our previous demo. We'll be reusing the same Nginx repository. I'll go to the container registry service via the developer services. And from the repositories and images drop down, I'll select the demo Nginx repository. At present, there is just one image with the tag latest in this repo. And as you can notice, this image has not been signed. This is an unsigned image. For this demonstration, I'll go ahead and pull a new Nginx image. Of course, it's an older version since we have already pulled a latest version. I'll use the docker pull Nginx : I'll specify some older version. Let's say 1.23.3 and hit enter. Well, it has pulled the Nginx image with the tag 1.23.3. Now I'll run docker images command to confirm the same. And if you notice, we have a new entry for nginx image with the tag 1.23.3, which has a different image ID. Now, as part of the process, I'll tag this image so that I can push it to the OCIR repository. I'll clear the screen first and run the docker images command again. I'll run the docker tag command, which is docker tag AC23. These are the initial letters of our image ID that we are tagging. As you can notice, the image ID is AC23. And then I've specified the FQDN for the path of the registry where the image has to be pushed. I'll go ahead and hit enter. Well, the prompt returned without any error, so we can confirm that the image has been tagged. I'll simply run docker images command again to check the same. And we have a tagged version of the nginx 1.23.3 image. As you can notice, the image IDs are same. Now I'll run the docker push command to push the tagged image to OCIR repo. Just to let you know, I am already logged into my OCIR repo using the Docker CLI. If you recollect from the previous demo, I had already used the docker login phx.ocir.io command login into my OCIR repo. The session is still active. I'll use the docker push and provide the FQDN for the image path where it has to be pushed in the OCIR. I'll hit enter. The push operation is in progress. Well, the image has been pushed. We can confirm the same by going to the previous tab and hit a refresh. Now, if I select on the drop down, you can notice that there are two images in our demo nginx repository, one with the latest tag and the other one with 1.23.3. And both these images are unsigned at this point in time. I'll select the image that we just pushed. Now, since I'll be signing the nginx image with the version 1.23.3, I'll also need its OCID to create the image signature. I'll copy the OCID of this image from the image information tab, which is available here. I'll click on the copy link, go to my notepad file and paste the image OCID. Now I'll be using this command as given on the screen to sign the image using the master encryption key and the key version in the vault service. The command is OCI artifacts container image signature sign upload, where we have to specify the compartment ID. I've already specified the compartment ID of my CTD OKE compartment. Then we have to specify the KMS key ID flag, where we replace this placeholder with the OCID of our master encryption key. I'll copy the master encryption key and replace the placeholder with the OCID of my master encryption key. Next thing that we provide is the KMS key version ID, which is the OCID of the key version used to sign the image. I'll replace this placeholder with the key version OCID that I had copied. Signing algorithm is one of the algorithms used to sign the image. In this case, it's SHA-224 RSA PKCS PSS algorithm. Image ID flag needs the OCID of the image that we wish to sign. I'll replace this placeholder with the image OCID that we copied earlier. And description is optional text of your choice to describe the image. I've just specified demo over here. I'll copy this command and paste it in the Cloud Shell terminal. I'll clear the screen first and paste the command to create the image signature for our image in the OCIR repo. I'll go ahead and hit enter. Well, the output returned without an error, which means our image in the OCIR repo has been signed. To verify the same, I'll go back to the container registry repository and hit a refresh. Now if I click on this drop down in the repositories and images section, you will notice the signed text appears besides the image that we just signed. In our case, it's Nginx image with the version 1.23.3. I'll select this image, and if I scroll down, we can see in the signatures tab, we have the entry for the image signature, where the description column specifies the description of the signature that was specified when we created the image. In our case, it was demo. The verification response column is the result of the last attempt to verify the image signature with the vault service. We haven't verified it yet, which is why it says unverified. Tags define the number of free-form or defined tags applied to the image signature, which is not applicable in our case. Date specifies when the image was signed and the image signature created. And optionally, to see more details like the master key, key version, and the signing algorithm for a particular signature, we should click on this action menu and click on View Key Details. This shows us the master encryption keys OCID, the key versions OCID, and the algorithm used for signing the image, which is RSA. I'll click on Close. Also, you can verify the image signature with the Vault service by selecting the Verify Signature from the Actions menu. I'll click on Verify Signature, and as you can notice, the verification response column now says verified. Here, the Vault service basically checks that the source of the image had access to a valid private key when the image was pushed, and that the image has not been modified since it was pushed. If both these conditions meet, the signature is shown with a verified status. And this provides confidence to the users or systems pulling the image from the registry that the source of the image is trusted and that the image's integrity has not been compromised. If needed, you can delete the signature just to indicate that the image is no longer considered trusted. And this option is available within the action menu. With this, we come to the end of this demo where we saw how to sign container images stored in the Oracle Cloud Infrastructure Registry using the master encryption key stored in the OCI Vault service. I hope you found this demo interesting. See you in the next one. Thank you for watching. Hello and welcome to this lesson on enforcing the use of signed images from Oracle Cloud Infrastructure Registry. In this lesson, we'll explore the imperative process of enforcing the use of signed images from Oracle Cloud Infrastructure Registry when deploying applications to a container engine for Kubernetes cluster. This practice is crucial for ensuring the integrity and authenticity of the deployed images. Let's get started. Here are key considerations to achieve this enforcement. Firstly, it's important to note that an image in OCIR can have multiple signatures, each linked to a different master encryption key. This multi-key association adds layers of security to the verification process. Now, a cluster's image verification policy comes into play, allowing administrators to specify up to 5 master encryption keys. This policy serves as a guideline for the cluster, dictating which keys are deemed valid for image signatures. Here's a critical scenario. If a cluster's image verification policy doesn't explicitly specify encryption keys, any signed image can be pulled regardless of the key used. Any unsigned image can also be pulled, potentially compromising the security measures. It's vital to understand the intricacies involved in identifying and referencing images within Oracle Cloud Infrastructure Registry. Here are essential points to guide this process. In Oracle Cloud Infrastructure Registry, an image is uniquely identified by its repository name, tag, and a distinctive alphanumeric digest. This triple identifier ensures precision, and accuracy in image retrieval and verification. On the screen, we have an image grab from the OCIR repository service, and from the image information tab, you can grab the full path of the image from the full path field. Also note that there is a digest field in the image information tab where you get to see the image digest of the image selected. In Oracle Cloud Registry, enabling a cluster's image verification policy introduces a specific requirement. Images must be referenced in the pod specification and manifest files using their digest and not tags. This shift to digest enhances the security and integrity verification process. Transitioning from using image tags to image digests mandates the modification of all existing pod specification and manifest files. To provide flexibility in certain scenarios, administrators have the ability to override the image verification policy. This can be achieved by adding a specific annotation to the pod specification. You can add annotations such as oracle.image-policy.kh.io/break-glass and set its value to true. Adding this annotations allows for deviations based on specific use cases or requirements. Let's break down the essential permissions required to bolster security measures within your OKE clusters. Here's a concise overview. To enable clusters to include master encryption key in image verification policies, you must give clusters permission to use keys from OCI Vault. For example, to grant this permission to a particular cluster in the tenancy, we must use the following policy. Allow any user to use keys in tenancy where request.userid is set to the cluster's OCID. Additionally, for clusters to seamlessly pull signed images from Oracle Cloud Infrastructure Registry, it's vital to provide permissions for accessing repositories in OCIR. The following example policy illustrates this permission grant for a particular cluster in the tenancy. Allow any user to read repos in tenancy where request.user.id is set to cluster's OCID. In conclusion, OKE container image security is the bedrock for safeguarding your containerized applications. We delved into the image integrity, trusted sources, and effective enforcement strategies. Stay tuned for practical demos translating these insights into actionable steps. I hope you found this lesson interesting. See you in the next one. Thank you for watching. Hello and welcome to this demo on enforcing the use of signed images from Oracle Cloud Infrastructure Registry. In this demonstration, we will see how to configure an OKE cluster to allow applications to pull only those images from the Oracle Cloud Infrastructure Registry that have been signed with specific master encryption keys. So let's get started. I've already signed into my Oracle Cloud account and this is my OCI console. Now, as part of this demo, I have already configured a few things as prerequisite. For example, I've already configured an OKE cluster which we'll be using. I have already created an OCIR registry repository with the name demo nginx, and we already have a signed image placed in the demo repository. This we had done as part of our previous demonstration. Now, to begin with, I'll show you the required IAM policies for enforcing the use of signed images. I'll go to the policies page by clicking on the navigation menu. I'll click on identity and security and click on policies. And as discussed in the theory lesson, I have the two policies in place which allow any user to use keys in tenancy where request.userid is set to the OCID of my cluster, which I'll be using in the demonstration. And there's another policy that allow any user to read repos in tenancy, where again the request.userid is set to my cluster's OCID. The first policy in the list allows the clusters to use keys from the OCI vault service. And the second policy allows clusters to pull signed images from the Oracle Cloud Infrastructure Registry repositories. Now I'll show you the container registry repository which is already in place. I'll go to the developer service, click on container registry. I'll make sure I choose the right compartment which is CTD OKE. Now if you recollect from our previous demo, we had created a demo nginx repository of type public and we had two images pushed to it, one with the version latest and the other with the version 1.23.3. And as part of our previous demo, we had signed the image 1.23.3 using the master encryption key in our OCI vault service. Now I'll click on the Kubernetes clusters link, and OKE public demo 2 is the cluster where we will be enabling the use of signed images only. I'll shift to the next tab where I have already set up the cluster access to my public demo OKE cluster. I'll use the kubectl get nodes command. And with this, I can confirm that I'm connected to my Kubernetes cluster. I have already created two pod manifest where I'm trying to deploy two pods on our Kubernetes cluster. One is the nginx pod with the version 1.23.3 and the other one is with the latest version. I'll open up the pod manifest that pulls the nginx latest image from our OCIR repo. This is the pod manifest where the kind has been set to pod. Metadata section defines the name of the pod which is nginx latest. Under the spec section, we have defined the containers field where the name for the container is nginx latest and the image field specifies the fully qualified domain name for our image lying in the Oracle Cloud Infrastructure Registry. And we have specified the image pull policy which is always, and under the port section we have defined the port that must be open on the container which is 8080. Close this manifest and go ahead and apply this manifest on the Kubernetes cluster. This is just to show you that the pod manifest, when applied on a Kubernetes cluster where the image verification is not enabled, it will run seamlessly. Now I'll go ahead and apply this pod manifest. Remember, I've still not enabled the image verification policy. Well, the output says pod nginx latest created. I'll use the kubectl get all command and we can confirm that the pod with the name nginx latest is up and running. Similarly, I have another manifest where I am pulling the image with the version 1.23.3. I'll open up the pod manifest first. And if you notice here, the image path has been set to the location of our OCIR repo and it's pulling the image version 1.23.3. Remember, this is a signed image, but since we have not yet enabled the image verification policy, this manifest should work. Now if I run the kubectl apply command, and hit enter, it says the pod nginx image with the version 1.23.3 has been created. You can confirm the same using the kubectl get all command, and both the pods are up and running. Alright, now I'll go ahead and delete these pods using the kubectl delete command. I'll clear the screen first. I'll delete the pod running with the version 1.23.3 and delete the one with latest version. Both my pods are now deleted. I'll confirm using kubectl get all command. Well, we don't see any pods running in the Kubernetes cluster. I'll clear the screen. Now I'll switch back to the previous tab, and here on the cluster under the resources section, I'll click on the image verification link. And the information tab says when image verification is enabled, you will need to ensure that the container images are signed by the required keys before they can be deployed to the cluster. The status currently says not enabled. I'll go ahead and click on edit image verification button and check this option which says enable image verification policies on this cluster. The moment I check the box, it prompts me to select a vault. I'll be using the same vault that I used in the previous demonstration, which is image signature demo, and I'll be using the MEK demo master encryption key. If you remember, I used the same encryption key to sign our nginx image in the earlier demo. Now, if you want to allow images signed by different keys to be pulled, we can specify multiple master encryption key. Just click on add another row and select the different master encryption key using which you have signed the images. And make a note that you can specify up to 5 master encryption keys in the cluster's image verification policy. In our case, we have just used one master encryption key, so I'll stick to that. I'll delete this entry and simply go ahead and click on Save Image Verification Settings. Well, the status of image verification has changed to enabled, and our cluster is undergoing an update process. Let's wait till we see the active status again. After a while, our cluster status now is active. Now that we have enabled our cluster to use its image verification policy, in the pod specs and other manifest files, we must reference an image using the image digest rather than the image tag. I hope you're liking this video so far. See you in the next one. Thank you for watching. Welcome back. Let's continue from where we left off in the previous part. I'll switch to the next tab where we have the Cloud Shell terminal running. And I'll open up the pod manifest for our nginx signed image, which is nginx version 1.23.3. And like I said, the container image must be referenced using its image digest rather than the image version. I'll delete the image version from here, and the separator that we use is @. Now I need the image digest for our nginx image with version 1.23.3. I'll head back to the previous tab and go to the container registry. I'll click on the drop down and select our signed image and copy the image digest from the image information tab. Digest is available here. I'll click on the copy link head back to our Cloud Shell terminal and paste the image digest. Also make a note that you will have to modify all existing pod specifications and other manifests if exist in order to use image digest rather than the image tags. In our case, we have already set up the image digest for our Nginx signed image. I'll save this manifest and hit enter. Now I'll run the kubectl apply command and provide the name of my manifest. I'll go ahead and hit enter. The output says pod nginx image with the version 1.23.3 created. Let's check using kubectl get pods command. Well, it says the pod is up and running. Well, just to confirm if we can pull an unsigned image or not, I'll open up the manifest for our unsigned image, which is pod latest.yaml file. Remember, this is an unsigned image. I'll simply replace the version latest with its image digest. I'll head back to the previous tab and select the unsigned image. Copy its image digest and paste it here. I'll save this file. Now use the kubectl apply command to apply the pod manifest. Manifest name is nginx pod latest.yaml. I'll hit enter. Well, we received an error from the Kubernetes cluster as the image that it was trying to pull was not signed, which is why it says this image has been forbidden. And the error reads image policy webhook backend denied one or more images, and the native Docker images should be signed. At least one image is not signed. Since the Nginx latest image we were trying to pull from the OCIR repo was not signed, this operation failed. Now picture this, having enabled a cluster to use its image verification policy, you might later have an urgent requirement for a particular pod to pull an image that violates this policy. In this case, we can go ahead and add the annotation to the pod specification file. Let me show you the annotation that we should add. I'll open up the Nginx latest pod manifest. I'll add the annotation under the metadata section, where the annotation is orkel.imagepolicy.kdes.io/breakglass, and the annotation's value is set to true. Once I've made the changes, now I'll go ahead and save this file and run the kubectl apply command to apply the pod manifest to our Kubernetes cluster. It says the pod nginx latest created. Let's confirm the same using kubectl get pods command. And there you go, we have the Nginx latest pod running the latest unsigned image on our Kubernetes cluster with the image verification policy enabled, using the exception that we had set through the annotation. You can also enable the image verification policy at the time of cluster creation. In this demo, I showed you an already created cluster, and then we went on to enable the image verification policy, but we can also do it at the time of cluster creation. I'll go ahead and demonstrate that to you. I'll go to the Kubernetes clusters service page. And let's click on create cluster. I'll go ahead with quick create workflow. I'll click on submit. Once you populate all the data for your cluster as per your requirement, you must click on the show advanced options, and here we have the image verification section where we have this option to enable image verification policies on this cluster. Once I check this, I'll have to select the vault and the master encryption key, which will be used to sign the images in the Oracle Cloud Infrastructure Registry repositories. Once done, we can go ahead and click on next and create the cluster. With this, we come to the end of this demo. I hope you enjoyed this demo and found it useful. See you in the next one. Thank you for watching. Hello and welcome to this lesson on encrypting data at rest and data in transit with the block volume service. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Let's get started. Let's take a look at some key points regarding data encryption in Oracle Cloud Infrastructure Block Volume Service. All block volumes and their backups in the OCI block volume service are encrypted at rest using the 256-bit AES encryption. Default encryption is performed using Oracle provided encryption keys. You have the flexibility to encrypt volumes and backups using keys you own and manage via the Vault service. Unassigning a key from a volume reverts to Oracle provided encryption keys. Encryption applies to both data at rest and paravirtualized in-transit encryption. Data moving between instances and block volumes is transmitted over a highly secure internal network. Enable in-transit encryption for paravirtualized volume attachments on VM instances. Some bare metal shapes support in-transit encryption for iSCSI attached block volumes. When configuring Kubernetes persistent volume claims backed by the block volume service, you have several encryption options to choose from. First, you can specify the master encryption key to use, and this is done by setting the KMS-key-ID property in the Kubernetes storage classes definition. You'll want to provide the OCID of a master encryption key from the Vault service. This ensures that your data is protected with the encryption key of your choice. Next, you have control over how the block volume is attached to the compute instance. You can define this attachment type by setting the attachment-type property in the Kubernetes storage classes definition. Your options include iSCSI or paravirtualized. This setting allows you to tailor the attachment method to your specific requirements. Lastly, you have the ability to manage in-transit encryption for each node pool within a cluster. You can enable or disable in-transit encryption as needed, and this can be achieved by setting the is-PV encryption in-transit enabled property, and this property can be configured using various methods like CLI, API, or console's configuration option. Let's understand with the help of a table the block volume encryption settings interaction. When is-PV encryption in-transit enabled property is set to true, and if the storage class attachment type property is set to paravirtualized, and the KMS key ID is set to OCID of the user managed key in the vault, both data at rest and data in transit are encrypted using the user managed keys. And if the KMS key ID for the paravirtualized attachment type is not set, both data at rest and in transit are encrypted with the Oracle managed keys. If the storage class attachment type property is set to iSCSI and the KMS key ID property is set to either the OCID of user managed key in the vault, or if it is not set, an error occurs which requires attachment type to be set to paravirtualized whenever the is-PV encryption in transit enabled property is set to true. When the is-PV encryption in transit enabled property set to false for the attachment type set to paravirtualized, and when the KMS key ID property is set to the OCID of the user's key, Data is encrypted at rest using the user managed key, but no in-transit encryption is available. Likewise, if the KMS key ID is not set, only the data at rest can be encrypted using the Oracle managed keys, but the data encryption in transit is not available. And when the storage class attachment type property is set to iSCSI for the isPV encryption in transit enabled property, which is set to false, here if the KMS key ID is provided, the data is encrypted at rest using the user managed key, and the data at rest is managed by the Oracle managed key when no KMS key ID is provided. But make a note that no in-transit encryption is supported whenever the isPV encryption in transit enabled property is set to false, either for para-virtualized attachment type or for iSCSI type. To provision a PVC on a block volume using a master encryption key managed by Oracle to encrypt data at rest and optionally in transit, you must define a storage class and set the provisioner to blockvolume.csi.oraclecloud.com. Also set the attachment type field to para-virtualized. You can then create a PVC that is provisioned by the storage class you have created. Having defined the storage class and created the PVC, you must set each node pool's isPV encryption in transit enabled property to true. You can do it using the CLI, API, or the node pools console interface. I'll transition to the OCI console, and from the node pools property, I'll show you where to exactly set the in-transit encryption for the node pool. I'm already logged into my OCI console and I'm on the Kubernetes clusters service page. I'll select one of the Kubernetes cluster and let's go to the node pool section. I'll click on the node pool name, and when I click on the edit button, this opens up the edit node pool window, and if we scroll down under the boot volume section, we have this option to use in-transit encryption. If I check this will set the isPV encryption in transit enabled property to true. To provision a PVC on a block volume using a master encryption key managed by you to encrypt data at rest and optionally in transit, you have to create a suitable master encryption key in OCI Vault or obtain the OCID of any such key. You must then create a policy granting access to the master encryption key. And having created a suitable master encryption key and policy, you then define a storage class and set the provisioner to blockvolume.csi.oraclecloud.com. Also set the attachment type to para-virtualized. More importantly, set the KMS-key-ID property and set its value to the OCID of the master encryption key within the vault service that you want to use to encrypt data. You can then create a PVC that is provisioned by the storage class you have created. And finally, having defined the storage class and created the PVC, you must set each node pool's isPV encryption in transit enabled property to true using either the CLI, API, or using the node pool's use in transit encryption option within the console. As shown on the screen under the boot volume section within the edit node pool window. To wrap up, in this lesson we covered encryption options in OCI block volume service, focusing on Kubernetes PVC configurations. The discussion included default and user-managed key encryption, attachment type settings, and in-transit encryption controls, providing a comprehensive guide for users to tailor their data security strategies. I hope you found this lesson interesting See you in the next one. Thank you for watching. Hello and welcome to this lesson on encrypting data at rest and data in transit with the file storage service. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Let's get started. In the realm of file storage service for provisioning persistent volume claims, the distinction between at rest and in transit encryption is crucial. By default, the service ensures data at rest is always encrypted using Oracle managed encryption keys. For those seeking to manage their own at rest encryption with personal master encryption keys, the process varies based on whether you are provisioning a PVC on a dynamically created new file system or an existing manually created one. To embark on managing your own keys, the steps involve creating a suitable master encryption key in OCI Vault or obtaining the OCID of any such key and establishing a policy to grant access to the master encryption key. To use a master encryption key from the Vault service to encrypt data in file systems, you must use the following policies. The first policy is to allow service FSS realm key prod to use keys in compartment where you specify your compartment name, where target.key.id is set to the OCID of your master encryption key, where FSS realm underscore key prod is the name of the file storage service user. The name of the file storage service user depends on your realm. For more information about realm, you must visit the regions and availability domains official documentation. Compartment name is the name of the compartment containing your master encryption key, and key OCID is the OCID of the master encryption key within the vault. Another policy that you must set up is to allow any user to use key delegates in compartment where you specify the compartment name, where all request.principal type is set to cluster and the target.key.id is set to the OCID of your master encryption key. This allows your Kubernetes cluster to use key delegates within the compartment where your master encryption key is present within the OCI Vault. Additionally, the file storage service offers optional in-transit encryption. If specified, data in transit is encrypted using Oracle managed TLS certificate, irrespective of whether the data at rest is encrypted using Oracle managed or user managed keys. To configure in transit encryption, the method varies depending on whether you are provisioning a PVC on a dynamically created new file system or an existing manually created one. The service provides users with the flexibility to tailor their encryption strategies to meet specific security requirements. Now let's take a closer look at managing data at rest for a new file system dynamically created by the CSI Volume plugin. And we'll explore both options, Oracle managed keys as well as own master encryption keys. When aiming to encrypt data at rest on a new file system using Oracle managed keys, the process is seamless. The file storage service automatically encrypts data at rest with Oracle managed encryption keys. To initiate the encryption of data at rest on a new file system, the first step is to create the file system. In this scenario, we are utilizing the robust security of Oracle managed encryption keys. To create a new file system that uses Oracle managed encryption keys to encrypt data at rest, we must go to the OCI file storage service, and under the create file system window, we must select the encrypt using Oracle managed keys within the encryption setting. Once you create a file system with the encrypt using Oracle managed keys enabled, the next thing is to set up the storage class definition file. As you set up the storage class definition, you must ensure not to include the KMS key OCID parameter. By doing so, you seamlessly leverage the default encryption capabilities provided by Oracle, enhancing the protection of your data at rest. For those opting to encrypt data at rest on a new file system using their own master encryption keys managed in the OCI Vault service, a straightforward procedure is available. Firstly, create the new file system using the option of encrypt using customer managed keys. This signifies your intent to utilize user managed keys for encryption. Within the OCI file storage service, when you create the file system, under the encryption setting, select the encrypt using customer managed keys option, and under the vault compartment, select the compartment where you've created the vault. Under the vault field, specify the vault. Then under the master encryption key compartment, select the compartment where your master encryption key is created, and under the master encryption key field, select the MEK that you had created. Once you create a new file system with the desired setting, the next step is to set up your storage class definition file, where you particularly set up the KMS key OCID parameter and specify the OCID of your master encryption key from the vault service as its value. To wrap up, in this lesson we covered how to set up encryption for data at rest and in transit on a new file storage service using the Oracle managed key as well as user managed keys. I hope you found this lesson useful. See you in the next